I'm Weitao from Rice University, and thank you for Silicon for introduction, and thank you for Hassan with a very great talk. So our talk is maybe related. We will introduce our paper RDC, which is a novel network architecture at the edge. So this is a joint work with Dingming from Bytedance, and also Sushovan, Afsaneh, Professor Chen, and Professor Eugene from Rice. So firstly, we all know that most of the data centers, their servers are organized in racks. And on top of each racks, there will be Tor switches. So those Tor switches will be used to connect all the servers under the same rack. And the reason to use that, because it can provide independent power supply, and it has reduced the cabling complexity and reduced the cable length. But there's a common but not so favorable design, which is oversubscription. So for a non-blocking network, the number of uplinks and the number of downlinks should be the same for the same Tor. But to reduce the cost of building a very expensive non-blocking network, many data centers are trying to do an oversubscription, which is the uplinks are smaller, have smaller bandwidth than the downlinks. But according to our investigation of the Facebook trace or Meta's trace, so there is a large amount of inter-rack traffic in the cluster. And you can see in the figure, this shows the source and destination of the traffic. You can see there are many traffic. That nearly 96% of traffic are inter-rack. So this makes the Tor becomes a bottleneck of the inter-rack traffic. Then we dive into the trace, and we find out one of the most important key observation, which is that the traffic are skewed at the server level. Means during a short time period, we can find many server groups, and the communication are very intensive between those servers within that group. But those servers may split across different racks, so that makes you have a very high inter-rack traffic. So with this observation, we ask a question: what if we can regroup the servers to let those servers to be under the same rack or same Tor? So you can see that after regrouping the servers in the Facebook trace, we can localize most of the inter-rack traffic. So now we only have 38% of the inter-rack traffic. And you can see that in the line showing the figure, most of the traffic has been localized to be under the same rack. To further show the power of regrouping, we give 4 examples, and we show the difference between the original rack and after regrouping. So firstly, which is common, that jobs may be fragmented across racks. And what we can do is that we can try to put all the servers with the same job under the same rack. And you can see we reduce the number of communications from 3 to 1 in this case. And the second example is that the traffic patterns may change over time. Like a fixed topology can only optimize for one pattern. But now, if we can change the topology according to the traffic pattern, we can optimize both patterns. The third example is that some applications has very strict placement constraint. For example, when you write to an HDFS system, you have to place the third copy onto a different rack for redundancy policy. And in this case, you can see that we can also regroup the servers to write into a server under the same logical rack, but it's actually under the different physical rack. The last example is that many racks has different out-of-port traffic. So we can also regroup the rack to balance the out-of-port traffic. So for this key idea, we present RDC, the rackless data center, and we will introduce each architecture and also the control algorithm, and then we'll show the evaluation on both testbed and simulator. So RDC's key building block is circuit switching. Circuit switch has many unique benefits, like it has very high bandwidth, very high port count, and is also more power efficient than packet switches. Most importantly, it is reconfigurable, and it can change the connections between ports to change the topology. So previously, circuit switches are widely used to build a reconfigurable network core, like RotoNet and Sirius. But RDC was trying to build a reconfigurable network edge. In this simple example, if we connect 2 TORs and 2 servers to the same circuit switch, by changing the connection, we can exchange the servers between those two TORs. So more TORs and servers can be connected to the same circuit switch to achieve more flexible reconfiguration. In our view, ultimately, for each RDC port, we should use one or more circuit switches to connect all the TORs and all the servers in the same port, so that we can regrouping all the servers in that port. To guide the configuration, we have a RDC controller which works in 3 steps. First, to obtain the flow pattern, and then determine the optimized topology, and then configure the network to be the new topology. To collect the flow pattern, we have 2 modes. RDC can work in a proactive mode, which is the application can send the traffic demand to the controller, or it can directly send the topology to the controller if this port is only used by that application. In a reactive mode, RDC will monitor the flow counters on the TOR, and it will estimate the demand of each flow, and so that we get the demand estimation. So in the second step, we will optimize the topology. So for RDC port with only one circuit switch, we use a BGP algorithm. So the edge weight represents the traffic demand between 2 hosts. So by partitioning the graph into several subgraphs, we can maximize the edge weight within the subgraph at the same time. We can divide the whole port into several logical racks. And for a port with multiple circuit switch, on top of this algorithm, we only need to add one extra constraint, which is the number of links between a TOR and any circuit switch should be fixed. To reconfigure the network, we will reconfigure both the circuit switch and the routing rules on the TOR switch to change the topology. And you can see more details in the paper about this part. To evaluate RDC, we built a real testbed with optical switches and 16 servers, which forms 4 logical racks. As we introduced, the HDFS write operation needed to place a third copy onto a different rack. And you can see that in this case, the job placement, like a SIMBAD, it's hard to optimize the performance because it cannot overcome this constraint. But RDC will regroup the servers as the figure shows, and they will let HDFS know about this topology so that the application can place the third copy on the same logical rack, but on a different physical rack. So in this way, we can localize all the traffic, but without violating the policy of HDFS. So you can see that in this way, RDC can achieve similar performance with a non-blocking network. We also evaluated 2 other applications to show the benefits. For the memory cache D, RDC can mitigate the imbalance problem and improve the throughput and also reduce the latency. For distributed matrix multiplication, RDC can reduce the communication time for both types of the communication pattern. For simulation, we have a much more larger scale with 512 servers in 16 logical racks. So we use HTSIM. So this is a packet level simulator with TCP protocols and ECMP protocols. So this is a simulator also used by NDP. So first, we'll compare RDC with previous work. We mainly compare with two of them, which is one is see-through, one is RotoNet. So see-through is mainly, its main idea is to add an additional link between the TORs. So it is best for serving a small number of hot TOR pairs. So you can see the red link, those are hot TOR pairs. You can add a link between them to accelerate the communication. And for RotaNet, this is a network core with a rotating topology. This figure is not so easy to digest, but I can give you a briefly summary, which is RotaNet is best for serving uniform traffic among all the TORs. And depending on the link bandwidth and the core network bandwidth, we have a non-blocking see-through and non-blocking RotaNet and a 4-to-1 also subscribed see-through and RotaNet. We tested 3 different Facebook trays, and you can see RDC has shorter flow completion time in most of the cases. The reason is that RDC benefits most of the intensive communicate servers, and the Facebook trace exactly follows this pattern. And as a counterexample, you can see on the right-hand side, for the Hadoop trace, the traffic pattern is more like uniform, so that in this case, the RotaNet can have a similar performance with RDC. In a second set of baseline, we compare RDC with non-blocking and also a different version of RDC. I will especially mention this one-time RDC. This means we will only apply RDC's algorithm for one time, means we only change the topology once. And in the result, we can see that the RDC has better performance than one-time RDC because the traffic patterns are changing over time. So every time when the traffic pattern changes, our topology will change accordingly so that reconfiguration frequency will benefit the performance. And RDC achieves similar median FCT with a non-blocking network, but the tail is slightly longer due to configuration downtime. In the last, we will have our energy consumption analysis. So we compare RDC with the non-blocking network. And we show the relative performance per watt result for RDC. And you can see that for a 4-to-1 oversubscribed RDC, it has more than 2 times improvement in terms of the energy consumption. So for this, we summarize our paper. We proposed RDC, which is a novel network architecture that will logically regroup the servers and remove the rack boundary. It has a substantial performance benefits for real-world applications, and it consumes less energies than non-blocking networks. And I think this concludes my talk, and I'm happy to take any questions. Thank you.